just shut up and... Yes, sir. Well, if you worked it, if you just worked, as long as I can see the mechanical part, like where you wrote down the antiderivative, had the two limits, and then plugged in. If you just like turned in a paper that had the numerical answer, that's not what I wanted. Yeah. Yeah, that's fine. Yeah. It's last call for test, redo, last call. Okay, so so far we've been doing these, like where we ended was the solids of revolution, right? We basically had a region and we wanted to revolve it around an axis. And from what I saw in the test, I felt like a lot of you did pretty good with it. Like, at least with the general idea. Some of the drawings were outstanding. Some of you mixed up the order, but it seemed like you were kind of getting there with it. And I think if you work through a few more examples in that section, you'll start to really like nail it down. So I'm going to say I'm done with 7.2. All right, and I'm going to move on to 7.3, and just briefly through 7.3. 7.3 has to do with kind of a problem we're going to run into with trying to revolve. So we're still revolving, but just let's see what happens. So I've kind of pre-wrote some of this stuff. Find the volume of the region bounded by y equals the square root of x and y equals x squared when it's revolved around the y-axis. Okay, so I'm trying to take this region. I already drew it out for you, the yellow region. I'm trying to revolve it around the y-axis, which I have my rotation here. All right, and so what do we need to do to solve this? Get our rectangle. It's horizontal, right? Because so far, every time we've rotated, our rectangle is rotated around this axis, so our rectangle is perpendicular to the axis of rotation, right? So far, the rectangle has been perpendicular to the axis of rotation. Perpendicular axis of rotation. And anytime our rectangle is horizontal, we know that our integral will have what with respect to dy, right? So it'll have dy. If we have dy in the integral, that means that both of our equations must be solved for what variable? X. Yes? Okay. So what we need to do, since the rectangle is horizontal, we need to solve each equation for x. So all I do is I just go grab those, take my y equals x squared, take square root of both sides, and I only have to use the positive one, not the negative one. Why? This was the original problem, right? Y equals x squared. Here's my region. Yeah, when you do it this way, x equals, when it was plus or minus root y, that would have given you plus root y is this one, minus root y is this one. So you don't really need the minus root y to get your region. Do y'all see that? And then the other equation, which was the square root, y equals square root of x, to solve that one for x, you square both sides, and you get y squared, which should be a parabola, shouldn't it? But I only need the top part of it. The bottom part comes this way, like this, right? So I only need the top part for that region. So I've solved both of these for x, and then I have to identify what? Once I've done that. The C and D, okay. I was going to do the outer and the inner first. It doesn't matter. Let's do outer and inner first. So if I come down here, here's my rectangle sideways. Here's my inner function. Here's my outer function. And the integral will be integral from 0 to 1. So the C and D, I guess I already got it. I think I got it just by looking at the graph, right? You can kind of tell from there. How would you do it, though? Set them equal to each other, right? So I've got the 0, 1. It's pi outer squared minus inner squared. The outer one is the square root of y, right? That's this red one. That was the square root of y. And then the inner one was the y squared. Square them both, and that's it, right? And that's pretty much the setup of the integral. So nothing new here, right? This is all stuff we've seen before. No questions? Okay, let's look at a problem which we would get stuck with. Okay, find the volume of the region bounded by y equals 4x squared minus x cubed and y equals 0 about the y-axis. So I already put the picture up here for us. Y equals 4x squared minus x cubed. There it is. It's this nice little polynomial function like this. And then I've got my y equals 0 here, and I want to rotate it around the y-axis, which is here. So if I'm going to rotate around the y-axis, my rectangle should be perpendicular to that. And what's wrong with that?
It's touching one. It's not touching both.
That's right. The outer function and the inner function are what? The same curve, right? It's the same curve. Like the outer radius and the inner radius are the same, touching the same curve. And so if you try and take one and subtract the other, shouldn't that be 0? So that's the problem with this. When we look at this, that's what I was saying. What's wrong with this? Basically what's going to happen is when we take outer squared minus in squared, we're going to get 0 because it's going to be the same function, the red one. Do y'all see that? So is there any other way I can handle this then? How do you mean?
Take two different sections of it, you split it in half, the shaded region.
How would you like to split it in half? I think I know what you mean. I think you mean like
From 0 to 2.
like here, like split it right there. Yes? Do y'all see what is being suggested here? Like take this line and then go from that line below, right?
Yeah.
Do that, and then add to that the volume you get when you take this outside and use that as your inner radius. So two separate integrals.
Create a new function of like, this would be like x would equal 2 or something.
Okay.
And then you substitute to where there's no outer function, and you do it in two different sections.
Yes, I got you. I agree. We could. The challenge I would see with that would be, how do you find where this lowest point is? Calculator. How do you? Because you would need that. You wouldn't just pick 2 because you have to pick.
It would just be like a
It would have to be the very bottom of that,
yeah.
right? So how would you get that very bottom? Anyone?
That's the lower maximum.
That's a minimum point. How do you find the minimum of a function?
So lower minimum.
Take the derivative, set it to 0. Then you could do it's some Cal 1 stuff, right? Look at where it's decreasing, increasing. So it would take some work to get that point, but I agree we could do it.
Yeah, that's probably a lot more work than what we need.
Yeah, so, and if I made this function more complicated, like let's say I made it come like this and then go down, and then go back up and down and back up and back down and back up, like oscillate, you'd have to do it, like I could make you do it a dozen times that way, right? It would be pain. So is there another way? Well, there are certain problems, not almost every problem, 90% of the problems pretty much. Well, I don't even know if I should say 90%. Forget percent. A lot of the problems you would forget, I mean, that you would get in a class, in like an engineering class, a lot of them, anytime you'd have to revolve to get a volume, you can do it the ways I've shown you. But there are some like this that just don't revolve easily. You see what I'm saying? Because of this scenario. So because of that, we have a new technique to do this. And it's called, so this is a big question mark, like we are stuck here, like how are we going to do this? So the new method that we are going to use is called the method of shells. So what we've been doing, remember when we were doing 7.2 to get the volumes, we revolved those things around. We took the rectangle, we revolved it around some axis, right? And it created this thing that looked like a hollowed out washer. Remember that? That's the idea of rotating a rectangle around an axis that's perpendicular to it. You get this washer, don't you? This other method, the method of shells, takes a different approach. So let's say I want to take the same function, that same region. That's it blown up real big, right? That's the problem we were just doing. And I want to rotate that around the y-axis like this. Instead of taking horizontal rectangles, I'm going to take vertical rectangles. And I'm going to take that vertical rectangle and I'm going to wrap that around the y-axis. Now the advantage to this is if we take a vertical rectangle, don't we know the top and bottom? Like it's not the same function? But what does it look like when you wrap that around the y-axis? Because it doesn't look like a washer. Yeah, I don't know what we want to call it. Let's point out some things before we wrap it. The distance from the axis of rotation to the rectangle itself is x. Now that's supposed to be an x there. It doesn't come out very good here. That's an x, okay? That's the distance. That's the distance from the origin to the rectangle, x. The height of the function is the top minus the bottom. What's the top function? Y equals 0 minus the bottom function, which is the cubic polynomial, right? So we have the top and bottom. We have the distance from the axis of rotation to this rectangle. Now, wrap it. And when you wrap it, you get this shape right here. It's not a very good picture. But do you see it? Do you see that wrapped around the x-axis? I'll try it again. Oh, wow. I need to sit down. It's basically something like this, right? Now, it has some thickness to it, though, doesn't it? So what does that look like?
Looks like you took the washer and just put it as a cover.
What is it? It's like this, right? Kind of. But it's hollowed out, right? Calamari? Who said calamari? Someone say calamari? I do too. That's what makes me think of calamari. All right, so it's this hollowed out, well, we call it a shell. That's what it's called. It's the method of shells. This thing is a shell. All right? So do you remember when we did the washer? Well, the way we came up with the formula pi outer squared minus inner squared was to say, well, what's the volume of a cylinder? And the volume of a cylinder was pi r squared h, wasn't it? So now we need to come up with a formula that we can use for the volume of a shell. Let me help you. What you can do is you come in here with some scissors and you cut the shell, just one edge, and you open it up and you lay it out. So it's kind of like we have our shell like this, right? We come in here, we cut it, and we open it up like this. What's the volume of this? Well, now it looks like this, doesn't it? Now it looks like this, laid out. And that's basically like a three-dimensional rectangular box. Three-dimensional rectangular box. The technical name of a three-dimensional rectangular box is a parallelepiped. If I start throwing that word around, people are going to be like, what? That's a parallelepiped, three-dimensional rectangular box. So what is the volume of something like that? Length times width times height, right? That's the volume of that. Stephen Ramirez? So if the volume of that little piece is length times width times height, I'll put it over here in red. The volume is the length times the width times the height. Tell me about, we'll do the easy ones first. How wide is this.
Oh no. If you're taking it
Yeah,
that way.
yeah, this way, this little piece right here,
Oh, that piece is
dx,
Yeah.
right? Does everyone see that? That was the thickness. This piece right here got wrapped around. How wide was it? Well, the width of our rectangle has always been dx, hasn't it? Because it's vertical, dx. So I know the width is dx. I'll put that over here. How high is the function? Or how high is the rectangle?
The upper minus the lower.
It's the upper minus lower, isn't it? I'll just put that here. Upper minus lower. I'm not going to put squared, right? No, because this is not a cylinder anymore, right? This is a box thingy. How long is it? How long is it?
But isn't X just in the middle? So it'd be
X is just the what?
What?
X is the radius, isn't it?
So it'd be 2? It's 2 pi x.
There you go. If the radius, if we look at this shell as a circle, right? Then when I cut it open and lay it out, the length is actually the circumference of the circle, isn't it? And the circumference of a circle is 2 pi r. But our radius is x. So the length of that rectangular box is 2 pi x. Did y'all see that? So this is 2 pi x. So let's try and come up with a general formula then that we would have.
For the rectangle thing?
What would the volume of this, of just this piece, just this right here? What is the volume of just this?
2 pi x.
The volume would be 2 pi x times upper minus lower dx. Yes?
I find that you have the integral of c.
So, and then if we want to add them all up, you want to take an integral, don't you?
That's just for that one?
That's just for that one rectangle got spun around, right?
Yeah.
You want to spin all of them. You want to come back up here to your picture, and you want to imagine doing an infinite number of rectangles, right? Infinitely many, spinning all those rectangles all around the y-axis. So to add all of them up, integral. From where to where, though? Yeah, do we do C to D or A to B?
It's horizontal to upper.
Think about what's changing in the problem. What's changing is where the rectangle is positioned, right?
Oh, it's the y's. Yeah, y's. This is A to B.
What's changing?
The x.
The x. You start at where? Where does your first rectangle start? At an x value of 0. And then what starts happening? You start moving around, moving out, drawing all these rectangles, and you let x go all the way to where? 4. So we will go from A to B. We've always reserved A to B for x values, right? And C to D were y values. So our general formula, okay, so I'm going to go to a general formula. And I'll draw a little picture just above it of what we're doing. We have an axis of rotation which is vertical, don't we? Like this. We have a region that's like, I'll do it in 2 different colors. Our region looks something like a blue one on top of a red one like this. Let's put my x-axis down here. What do my rectangles look like? Vertical or horizontal for this? Vertical. Then if we wrap that around, the general formula will be integral from A to B of 2 pi x upper minus lower dx. That's a general formula.
Would we always take the 2 out, or do
The 2 pi could come out of this integral. Yep. So that's very different than the last formula, right? But it gives us the same volume. Okay? Any questions? Yes.
So how would you know when to use the previous washer method or the shell method?
How would you know?
If you revolve around the X or the Y, right?
Not necessarily.
If we have the same
It depends on if you run into this situation where you're trying to draw your rectangle perpendicular to your axis of rotation and the outer and inner radii are the same function. If that's the case, then you want to use shells.
I guess because on the one you just drew, it had different ones, right? Different functions.
Yeah, wait, on which one? The one before this?
Yeah, the one you just drew, it had the same.
Oh yeah,
Had different functions.
that's right. Well, on the last one I drew right here. Yeah, I was just trying to give you like a general picture. If your region is over here, you're trying to wrap it around this axis. You can't go sideways with rectangles, can you? Like look at that rectangle right there. What's wrong with that? It's got the same on top and bottom, so you can't use it. Does that kind of make sense? So you use a shell instead. No? You're just being agreeable. In order to have a rectangle have an upper and a lower or an outer and an inner, the outer and inner have to be different. They can't be part of the same curve. If I try and draw a rectangle right now sideways here and wrap that around as a washer, then the outer edge and the inner edge are part of the same curve, which means I can't. You have to have a different one on the out as you do on the in. What was the other question? Yes.
Rectangle be vertical and use the previous equation.
Why can't the rectangle be?
Why couldn't it just be vertical since the beginning? And then you can't use the previous equation? Like,
What do
I
you
don't understand why you have to do the shell thing.
on?
Because when you saw the problem, the rectangle was horizontal, so it was touching both the same curve.
Yes, here.
But why couldn't it have been vertical?
If it was vertical, how are you going to wrap it around the y-axis?
Well, I don't know. That's what I'm asking.
Well, that's what we did. We made it vertical. We made it vertical here, but we said if we wrap it, it's not the same formula because the geometric shape when we wrap it is not a washer.
Oh, okay.
It's a shell.
Okay.
So the formula for that washer is different than the formula for the shell. For the washer, it's pi times outer radius squared minus inner radius squared. Remember, the outer radius squared was a solid washer minus the inner radius squared was the inside piece. You subtract that from that and you get a hole in it, right? So it was the outer squared minus inner squared times pi. That's what you would get if you wrap a rectangle this way, like vertical rectangle around the x-axis. I don't know if that answers your question. So the only way you could use washers on this problem is if you're trying to wrap something around like y equals 0, like the x-axis. As soon as you want to try and go around the y-axis, it's not going to happen. Yep. I think we probably should do an example. What do you think? Just work through one real quick? Okay. Let's do find volume of region bounded by y equals x squared minus 4 y equals x with x greater than or equal to 0 about the y-axis. Can someone shut that door, please? So first thing is do a quick graph, right? Just so we know what we've got here. So the graph would look like this. We've got the parabola y equals x squared minus 4. That's 1, 2, 3, 4 down on the y-axis. It opens up, hits at 2 and negative 2. Is it too much for me to expect that you could get that? Like, that's okay? All right, and then y equals x. Y equals x is the diagonal line. Like something like that. I'm a little off on this, but close enough. That's y equals x. And what's the next region? I mean, what's the next thing? X greater than or equal to 0. What does that mean? X greater than or equal to 0. I'm only on the right side of the y-axis. So my region is actually this right here only, right? Everything to the right of the y-axis. Now, let's just look at this for a second before I go any further. Could you do washers? Could you do washers? I want to wrap around the y-axis. My y-axis is right here, so I'm rotating around this way. Could I use washers? If I'm going to use washers, my rectangles have to be perpendicular to my axis of rotation. So can I put a rectangle right in here? Do you have an outer and an inner? Yes. Well, the outer is this one, right? And the inner is just 0. But the problem is that when I get over here, it changes. Your outer and your inner change, don't they? As soon as you pass the x-axis. So not only would you have to solve both those equations for x, right, to go sideways, you would have to solve both those equations for x, but you would also have to do two integrals, one that went from here to here, and then one that went from here to here. Do y'all see the trouble in that? So it could be done, but with shells, we can wipe it out all in one problem. Why is it that we can knock it out with shells in one problem? Our upper and lower are the same the whole time throughout the entire region. So if I come in here and I draw my rectangle vertically, like this, then the upper and lower the upper is always what? X, and the lower is always x squared minus 4, isn't it? So I'm going to use shells here. And I'll draw my axis of rotation. I'll draw my rectangle out here. Notice my rectangle runs parallel to my axis of rotation. That's the big difference between shells and washers. Washers, your rectangle is always perpendicular to the axis of rotation. Shells, your rectangle is always parallel. Is that a question?
That's pretty much what I was asking. Perpendicular,
With shells, it's always parallel. Yes. I'm going to put in, on my picture over here on the side that I've got going with my rectangle, I'm going to put in the upper and lower in the colors first. The upper one is the red one, isn't it? It's the line coming through there. And the lower one is the blue one. Do y'all agree with that rectangle? That's what I've got. The line is on top, the blue is on bottom. So let's now tell me the height of that rectangle. What's upper minus lower? X minus the lower function, which is the x squared minus 4. Does that make sense to everyone? Any questions? That's the upper minus the lower is my height. What else are we going to need? 2 pi x is going to go in my integral, but I also need to know a and b, right? I need a and b. I think you can tell by the picture, 0 is where it starts. Where do they hit each other? Where do they hit each other? So I need A and B. A is 0 just by looking. Got that. But I have to set them equal to each other. X squared minus 4 equals X. Right? That's what I'm supposed to do. Which means X squared minus X minus 4 equals 0. And that doesn't factor. So you have to use quadratic formula. Right? I'm not going to go through it, okay? You use quadratic formula, you'll get two x's. One of them is going to be negative and one's going to be positive. You can tell where they hit each other, right? They hit each other here and they hit each other here at those 2 points, right? So one of them is a negative x value, you're going to chunk that one. The other positive one is the one you want. So your integral is going to go from 0 to some weird number, okay? This was more about you just understanding the setup. So here's my integral. It is integral from 0 to something, okay, that I'm going to get from solving that equation. Then what? 2 pi x. Upper minus lower? X minus x squared minus 4 dx. So that integral would represent the volume of that region rotated around the y-axis using the method of shells. Any questions? Sure?
What do you say about when it's perpendicular to something, it's shells? I want to write that down.
Okay, if your rectangle is perpendicular to your axis of rotation, then you're going to have to use washers. If it's parallel to your axis of rotation, well, I don't have it up there, then it's going to be shells. Yeah. I didn't want to spend this much time on this, but what about this real quick? How about this region? Let's do y equals x squared minus 4 again. Let's do y equals x. Let's do x greater than or equal to 0. And let's do it about x equals -3. So I've moved your axis of rotation now. That's the same region though, isn't it? That we just got? So my picture is going to be pretty quick here. Our region was, the blue one came up like this, the red one was like this, and our region was in here, right? And we want to go about the line x equals -3. Where is x equals -3? Vertical or horizontal line?
Horizontal. I mean, vertical.
Vertical line through -3? Does that region being wrapped around the y-axis have the same volume as it wrapped around that line? Or are they different volumes? Do you see if there is a difference? Like if I take this yellow thing and I just spin it around on this y-axis all the way around, then I get like a solid shape, right? I mean, it's a solid object. It's got kind of a hollowed out inside. But if I wrap this thing around this line, I could actually put my hand in between the solid, right? It would be the solid shape, but it would have a hole through the middle. You'll see the difference between them or not? One looks like this. And the inside comes down. Oh, actually it comes down like at an angle. Like that's if you wrap it around the y-axis, right? But if you go around x equals -3, it's going to be like this. The inside is going to have an actual hole in it, won't it? No, absolutely not. This one has been spun around, and I can actually put my hand down in it.
It's a greater radius that you're
Greater radius, right?
The length is the 2 pi.
The 2 pi x is different.
Because x is bigger, just to get rid of the whole 2.
Do y'all see that these are completely different objects? So they should have different volumes?
The rotation.
Okay, so let's see. Do we still have the upper, lower shells method? Could we still do that? Let's look at our shell. We've got this, right? We've got our axis of rotation. I'm going to draw another picture down here. Here's our axis of rotation. Here was our rectangle. We still want to say upper minus lower, right? Is it the same upper minus lower?
Yes.
Same one, right? Which was x minus x squared minus 4. So that hasn't changed, right? That's still the same. Does A to B change? Does my rectangle inside that shape change? It still goes from 0 to something, right? Something has to change then. What changes?
Well, the distance.
The distance. See,
So it's not x anymore.
it's exactly the distance from your axis of rotation to your rectangle. That distance right now is no longer x. It's actually what?
X plus 3.
Exactly. Look at, I'm going to try and get an arrow in here to see it. That right there, that distance right there, from here to there, just that is x, isn't it? That little piece from the origin to my rectangle is x. But I want to rotate from here to the rectangle, which would be how far? 3 plus x. And the fact that it's negative doesn't matter because it's a radius, isn't it? It's a distance. So instead of my formula being 2 pi x upper minus lower dx, it's going to be 2 pi x plus 3 or 3 plus x. So it's integral from 0 to, that's still a question mark, 2 pi, but instead of x, that distance was 3 plus x. This is 3, and that is x. So 3 plus x, 3 plus x, and then my upper minus lower dx. So I'll highlight the big difference in this problem. The big difference in this integral is the 3 plus x.
So will that part stay the same, the x minus x squared minus 4 dx, so just the x change?
Just this. So what would happen if I said, instead of rotating around x equals negative 3, I said rotate it around about, let's say I rotated about x equals, yeah, give me a second, negative 10. Then what would the only thing that would change in this be? That right there would change to a 10 plus x. Right? Because what would happen is you'd have your axis of rotation, you would have your little region over here that you're rotating, and the distance between your rectangle and your region would actually be the 10 then plus the x. The question is really what would happen if it's like x equals 5? What if it's on the other side of the region? What is it? 5 minus x. 5 minus x. So I'll draw a picture of that one as quick as possible. If I take this region again, I'm just going to draw the region real crappy like this. There you go. There's my region. There's my rectangle. If my axis of rotation is over here at 5, x equals 5, then what's the distance from me to the rectangle? Well, if the distance from the origin to the rectangle is x, then distance from there to here is 5 take away x. Do y'all see that? So the only difference there would be 2 pi, in parentheses, 5 minus x, then upper minus lower dx.
If the rectangle was on the negative side, you would still add, right? It would be 5 plus x
if your region was on the other side, then it's still a distance. Yes. Okay, now I'm not going to, a problem that you would see like this on a test would be pretty much what I showed in class. I mean, because you could take all of these things and you could apply the same principle to a region that went sideways, like this region, if I wanted to rotate it around this. See, you can't do that region with washers, can you? No. So you'd have to go shells. But now everything's in terms of y. So your integral would be integral from c to d, 2 pi y, outer minus inner dy. I'm not going to do that, but I'm just showing you this can be extended now. All right, we're done with this. We're ready for a new section. The next section, I think it's 7. That's 7.3. I want to say it's 7.4. I'm just going to put arc length. I think it's 7.4. All right, so far, here's what we've done, like geometrically. In this class, here's what we've done. We started with the idea of area underneath a single curve, right? We did that. We were like, yay, that's just the definite integral, right? And then we went on, we said, hey, what's the area between two functions? What's the area between two functions? And we say, yes, we can do that. Well, we've been tested on. Doesn't mean we can do it, but we've been tested on it, right? And then after that, what did we do? What's that? Well, we've done more than that. Volumes, right? So we rotated these things around. So then we did volumes, where we take that thing, we wrap it around, we get some weird shape, and maybe we can find the volume of something wrapped around, right? I mean, that's what we've done so far. Areas under a function, areas between functions, wrap functions and wrap regions around x, y axis, different lines, and that's it. Now we're going to talk about arc length, which is pretty disconnected from all of these, right? Arc length has to do with the length of something. Length is a one-dimensional measurement, right? Area is two-dimensional. Volume is three-dimensional. So when we talk about arc lengths, it seems like maybe we should have started with arc length. It seems, I don't know, it just seems like maybe that would have been easier. But arc length, the idea is pretty simple. You have a curve like this, and you take, let's say from here to here, you take that curve, and let's just say it were string sitting on a board. I walk up there, I pull the string off the board and straighten it out and measure its length. Does that make sense? How long is it? That's the idea. So we're not measuring the area underneath. We're not rotating anything around. We're just pulling that off the page and straightening it and getting a ruler out and measuring it. I don't think I've looked at this in the book. So let's see if I can remember this. I should be able to. Okay, so what we're going to do is we're going to blow up one section of this, okay? Let's just like zoom in onto this one section and take a look at it. Thank you, thank you. So now I'm zoomed in on that one section. Now, that section is approximately a right triangle. Approximately, right? Would you agree with that? Almost? Yes, it has a curve to it. So would you agree that there's going to be a bit of an error here? But do you agree that that hypotenuse, which I'll do it in a different color, how about I do it in this darker purple? Would you agree that that hypotenuse is pretty close to the length of that curve? What would make it an even better approximation? If I zoomed in even more, right, and got a smaller triangle. And what if I zoomed in even more? Well, isn't that the same idea as taking a rectangle like we did with area? We said, how will we get better? Do more rectangles. More until what? You have infinitely many rectangles? Well, imagine me zooming in infinitely into that. Then I eventually, the error in that is so minimal that it actually, it becomes the true length. Because it's like a limit. It approaches something. Does that kind of make sense? Okay, so let's talk about how long this is. Well, let's first of all, let's label this curve. Let's call this curve y equals some function of x, okay? So that means I'll put an example next to it, even though I'm not trying to do an example right now. Y equals sine x, okay? So we have y in terms of x. It's a function of x. So tell me a little bit about this triangle. Let's look at it here. Tell me about the purple. It's a hypotenuse, right? It's the hypotenuse of a right triangle. Do you know anything about the other sides of that triangle? Not really, right? Isn't the base of this right triangle almost like the base of the rectangle from our pictures when we were doing areas? Isn't it the width? So wouldn't that be dx? Do you see what I'm saying? Like if we took that one rectangle, we said how wide is it? It was dx, right? Well, the width of this one zoomed in little section is dx. And how tall is it? Well, be careful because f of x is the whole way, isn't it? So I'm going to try and remember. Our triangle's up in this picture up here zoomed in. It's kind of hard to draw it in there. See my triangle all zoomed in up there? Yeah, f of x is from the x-axis all the way up. So it's not the height of the function. Is it? No. Well, what is it? How high? This is just a tricky part. I'm trying to get you to see it. Isn't this bottom left corner of the triangle, is how high the function is right here on that little piece right there. Do you see the little yellow piece? Right, that's this bottom corner. That's the height of the function. That's the blue at the left end, right? And then when you move a little bit this way, you move up a little bit, right? So if this is how much you change in x, isn't this how much your change in y is? That's your change in y, isn't it? That's how much your y coordinate changes by. You move a little over x, your y goes up. Yes? So that other side is going to be dy. And then by the Pythagorean identity, a squared plus b squared equals c squared, the hypotenuse would be what then? That purple would be square root of dx squared plus dy squared. Wouldn't it be? Isn't that the length of that one little purple piece? Isn't it? Approximately, right? Yeah. Now, what did we do? I mean, because that's all we wanted, right? Like before with the areas, we wanted, what's the area of the rectangle? With washers, we said, what's the volume of one of those washers? With shells, what's the volume of one of those shells? And then we start adding them up, right? We integrate now. Now, we want to integrate, and we got to be kind of careful here. We want to integrate from where to where? A to B, so I need to put my A and B on my picture. A to B. What's that? No, you'll see where the dy, what's going to happen there. Okay? Okay, now we have integral from A to B of, now we just want to add all those up, right? All those hypotenuse. How do you say, what's the plural of hypotenuse? Hypoteni? Hypotenuses? That's weird. I never thought about that before. Okay, so it's the square root of dx squared plus dy squared d what?
X. X because it's Z.
What do you think here?
17. I'm just kidding. X, Y. No, we can't do both. That's Cal 3, I think.
dx or dy? This is where things get kind of a little funky. What's that? Since we're going from A to B, it has to be dx. I mean, it's almost like, that's why we've always reserved the AB and the CD for different ways, because it helps us when it comes to things like this. Anytime you're going x values, you're changing your x from A to B. That means your integrals with respect to x. Let's just put that in here now, and let's just see what happens here. Because right in here, the highlighted dx in here and the highlighted dy in here, we need to address these still. Okay? What is our function dependent on? Let's go back up to, right here. Our y function is dependent on x, isn't it? Our y function is dependent on x. If y is dependent on x, what's the derivative of x? If y depends on x, so what's the derivative of x with respect to x? If you're treating x like your variable, what's the derivative of x with respect to x? 1, right? If I write, what's the derivative of x with respect to x? What's dx? It's 1. This has to, if you want to go back in Cal 1, this is implicit differentiation. When you're differentiating a variable with respect to some other variable, you have to know if it's the same variable, then it's 1. So since our original function is in terms of x, it's a function of x, this dx inside this integral is actually a 1. But then what's dy dx? What's dy dx? That's f prime. That's the derivative of the function, isn't it? Dy dx is the derivative of the function. So this is f prime of x. So the formula becomes integral, who has their book? A to B square root of what? Dx was 1, right? 1 squared? 1 plus f prime of x squared dx. Someone has their book? See that formula there? Is it there? Oh, I mean, yeah, that's it, right? It's on page 387. Okay. I hope there was a bigger lesson in this. I seriously, remember I told you I haven't taught this in like 5 years. I didn't look at this section before I came into class. That's the difference between knowing something and understanding it. Is deriving a formula. I'm not trying to show off or anything like that. I just really, that is the difference. That's the difference between a master's degree and getting someone to help you in a tutoring lab, right? Someone in tutoring labs can be able to show you the formula and apply it. Someone that understands this at a deeper level will be able to come up with the formula themselves without the book. So as engineers, you want to be the person who's not flipping into the book going, well, that you want to understand things at such a deep level that you are the one that can explain that. Do you understand what I'm saying? That's what I hope all of you can strive for, is a deep understanding rather than memorization. Okay, what is what do we do now? Get an example, right? We have a formula. Let's do a problem. Has anyone ever wanted to know how long the sine function is? Like take one period of sine, take it off the page, straighten it out. How long is it? Anyone ever care? No?
Constantly dream about that.
Not really?
Yeah, why not? Yeah. Haunts me in my sleep.
I'm going to take care of that nightmare right now. There we go.
This is why I signed up for Cal 2 right here. That's the only reason.
It's the top requested thing on my student surveys is, been dreaming about sine function for a long time. Okay, find length of, man, hold on a second. These problems are very tricky because if you don't pick the function properly, they become integrals that are nightmares. Like we can't just pick some arbitrary function right now and be like, oh yeah, let's just find its length. If you do that, some of the integrals would be impossible for you to get. So we have to be picky about the ones we use. So how about of the function, let's try sine x on the interval, let's do the whole period, 0 to pi. All right. That did come across sort of arrogant the way I said that about that formula, huh? I'm sorry if it did. But I mean, it's just true. I mean, it's just whatever you study, you need to want to learn it at that level. Where it's not just cookie cutter. Anyone can do cookie cutter, monkey see, monkey do. There are a lot of people who can do that. It's going for the deep understanding. All right. Here's our function, sine curve, right, like this. That's one period. I want to know how long it is, between 0 and 2 pi. So there's really nothing that you need in here other than what? I mean, what's the only thing you need to apply the formula? The function, and in the formula, you need its what? Derivative. That's it. So take the derivative of that function is negative cosine, or no, cosine. You're messing me up. Right, negative cosine x. Now we don't need dx because dx is 1. Right? Back when we were first learning derivatives, we took, what's derivative of cosine x? We said, what's derivative of sine x? We said cosine x. The reason we needed it in our integrals is because in our integrals, when we were doing techniques, is every time you'd make a substitution, then that d whatever could be something other than 1. So now we don't need it because we're back to like traditional, original Cal 1 derivatives. So my integral is going to go from where to where? 0 to pi. Then square root of 1 plus the derivative, which I just found, cosine squared x dx. Uh-oh. Well, it's already in trig form.
It would be if it was 1 minus.
Oh, yeah, we wish this was 1 minus, didn't we? Don't we? If that was 1 minus cosine squared x, that would be sine squared x, square root of sine squared x would be sine, and we'd be in business. But it's not. But it's not. So, like I said, you have to be careful when you pick these problems. You can't just arbitrarily pick a function and be like, yeah. Now, Wolfram Alpha and the TI-89 will do this, but I don't think we're going to be able to get this integral. But let's look at it. I mean, you can go ahead and compute it, but let's see. I mean, is there any technique that we know to do this? Let's go through what we would go through as a process. Basic substitution. Do you see something in its derivative there? Not really, right? You could, but if you do double angle on cosine squared, you'll get what, 1/2 plus 1/2 cosine 2x. You could put the 1 plus the 1/2 and get 3/2, right? But then you'll have like what, 3/2 plus cosine 2x, or 1/2 cosine 2x. Then what? You still don't have a basic substitution. I'm trying to help you eliminate what you can do here. So yes, you could make that power reduced thing, but then you still may be stuck. Integration by parts. The only thing you could pick for integration by parts is this whole thing for u and make the other piece your dv. But the derivative of this is going to be 1/2 times the root of that times the derivative of cosine squared, which is, oh my goodness. Did you do it? Did you integrate it? Okay, let me see. Oh. Yeah, do it without the limits of integration. Don't go from 0 to 2 pi. Just do the actual integral. We're going to have the computer just help us out, just to show you that we couldn't integrate this. So I'm trying right now the integral 1 plus cosine squared x dx. That's what we're trying, right? Yeah, the computer's going to give you an answer, because the computer can do this numerical integration. But how about, did it give you something yet? Or is it still thinking? Here, hold on. Yep, okay. Square root 2 e x 1/2. Okay, this right here is not the exponential function, okay? This is an error function. An error function, yes. It doesn't mean that there's an error, but there is a function that gives you error in problems. So, in other words, there is no closed form antiderivative of this function. We cannot find an antiderivative. What, did you get a numerical answer? Yeah, you can get a numerical answer, but you can't get a general antiderivative. Okay, they're two different things. The way your calculator computes it is two different ways. So, lesson of this story is that I said, hey, have you ever wanted to know what the length of sine x is? Seems pretty simple, right? Turns out that integral is almost impossible for us to do. It is impossible for us to do. The computer has ways of doing it, but that integral that doesn't look that intimidating is actually not something we can handle. So the book is going to pick problems that you can handle. So let me use one of these out of here. Can I again? Whose book is this? I'm just going to do one problem. So, all right, so let's do this one. How about the length of this curve? Y equals, find length of y equals 1/3 x cubed plus 1/4x on the interval 1, 2. So I'm not going to bother to graph this, all right? It's some curve sitting out there. Let me just make sure I don't have any domain issues. I'm okay, right? No domain problems. The only thing that would cause this function to have problems is 0. And I'm on the interval 1, 2. Okay, the length will be then what? Integral from 1 to 2, square root of 1 plus the derivative squared, right? The derivative squared. What's my f of x? This thing up here, right? So you need to find the derivative of that. Maybe we should do that on the side. I'm going to call it y prime instead of f prime. What's y prime? Derivative, not antiderivative, right? Go ahead. X squared. Uh-oh. What's the derivative of 1 over 4x? Negative 1/4 or 1 over 4x squared. Remember, 1 over 4x is the same as 1 over 4 times x to the negative 1. Bring that x back up. Take derivative, negative 1 comes out, x to the negative 2. Drop the negative 2 back down, or x to the negative 2 back down. Is that okay, everyone, with this? So that's going to go in here, x squared minus 1 over 4x squared, but then still what? Squared, then dx.
But it goes from 1 to 2, right?
Yeah, I don't know why I put 1 up there. What do I still need to do? I mean, like, when you look at that, does that look like an easy integral right now? That one looks somewhat challenging too, doesn't it? Let's square this thing, all right? Let's square the inside and see what happens. So integral, I'm going to do this way down here. Integral 1 to 2, square root 1 plus, now what do you get when you square that? You have to FOIL it, right? So x to the 4th minus, do I need to do it over here or? X to the 4th, what do you get on the next one? Oh wait, that's over x squared. Yeah, the x squareds are going to cancel out. So you'll get minus 1/4, minus 1/4 again. So minus 1/4, minus 1/4. And then our last term is what? Plus 1/8 x to the 4th. Do y'all see where I'm getting that from, multiplying those things out? That's all still underneath the square root. Dx. Now let's collect some things together. What's 1/4 or negative 1/4? Take away another 1/4. That's negative 1/2. Add that to 1, and what do you get? So when you put the 1 together with the minus 1/4 minus 1/4, you get a 1/2. So integral 1 to 2, square root 1/2 plus x to the 4th plus 1/8 x to the 4th dx. We're getting there. X 1 over 8. Ah, geez, I keep doing that. 1 over 8 x to the 4th. Yes.
Would it be 1 over 16?
On.
Like 1 over 16?
Oh, yes, thank you for catching that. This one, the 8/16. You're doing 1/4 times 1/4, well, negative 1/4 times negative 1/4, positive 1/16. What we do now, see, I'm showing you this problem because I want you to see this if you've never seen this before. A lot of these arc length problems are like this. So we've expanded everything out, right? Took derivative, put it in there, squared it, expanded, collect like terms. Now what we're going to do is get a common denominator and put all these fractions together. So what's my common denominator? 16x to the 4th. So what do I multiply the 1/2 by to get a 16x to the 4th? 8x to the 4th on the top and bottom, right? 8x to the 4th. So I'll have an 8x to the 4th on top, and on the bottom I should have the 16x to the 4th, right? What about the second one? What do I multiply by on top and bottom to get 16x to the 4th? I need the whole thing, don't I? Because that x to the 4th is really x to the 4th over 1. So what do you get in the numerator when you multiply x to the 4th by 16x to the 4th? 16x to the 8th over 16x to the 4th. Plus, do I need anything on the last one? No, so it's 1 over 16x to the 4th dx. Any questions there? Integral 1 to 2. Okay, since they're all over the same denominator, I can put 16x to the 4th on the bottom. On the top, I'm going to put it in descending order. 16x to the 8th plus 8x to the 4th plus 1 dx. Y'all still there? We're almost done. I'm going to let y'all go. Integral 1 to 2, square root. Now, the numerator of that fraction is a perfect square trinomial. It's 4x to the 4th plus 1 squared. In other words, if you factor out the numerator, if you factor it, it turns into 4x to the 4th plus 1 times 4x to the 4th plus 1. Do y'all agree with that? Yep. And now you have a fraction, and you can take the square root of each one. So what's the square root? I forgot my dx here. That should not be under the root. So it's more like this. Integral 1 to 2. What's the square root of the numerator? Like when you take the square root of something that's squared, the squared cancels, doesn't it? So that should just be, what? 4x to the 4th over, plus 1 over 4x squared dx. Yeah, much nicer. Now split this into two integrals. Integral 1 to 2 of the 4x to the 4th over 4x squared plus the 1 over 4x squared dx, right? I'm just going to split that up into two fractions. The first one becomes what? X squared. The second one is 1/4 x to the negative 2, isn't it? Yeah, I don't know why I keep doing that. So all I did y'all see what I did on there? 4x to the 4th over 4x squared just canceled out the 4's. X to the 4th over x squared is x squared. On the other one, I just wrote it as a 1/4, and I brought the x to the negative 2 up. And that's because now I can just use power rule on each one. This is going to be, I'm ready for my answer, so 1/3 x cubed minus 1/4 x to the negative, oh wait, I'm doing antiderivative, x to the negative 1, evaluated from 1 to 2. I'll let you take it the rest of the way. But you would plug in 2 now and plug in 1, subtract the two answers, that's your length. That's a lot of work to get it to an integral you can do, right? All the problems in the book can somehow be manipulated out to an integral you can figure out. That sine one I did in the beginning was just to kind of illustrate it's not as simple as it might look, and to be careful. I'm going to send you a homework assignment later on today, all right? I don't have it ready to roll. So check your email. It'll be something at a 7.2 with shells and 7.3 with arc length. That is 7.3, right? No, it's 7.4. 7.4. Have a good weekend, everyone.